All right, today we're going to start chapter 4. This is polynomials, and this will deal with a lot of factoring, some applications. Um, the reason that we have such a major focus on polynomials is because, well, one, they're very useful in modeling a lot of real world scenarios, so being familiar with them is going to be very useful throughout mathematics, and you'll be able to take a lot of scenarios and find a function a lot of times that is a polynomial that will model those situations. So we're going to deal first thing with zeros of polynomials and solutions. This is what ends up being the end goal a lot of times is I want to know where, well, I'll get to that in a minute. Graphing factored polynomials and finding zeros. Finding the zeros is probably the most familiar thing for polynomials with all of this. So the zeros of a polynomial is the same thing as saying what is the root of a polynomial or what is the solution to the polynomial equaling 0. So a number that we call k, and k can be complex, which means it can be a real number or it could be something like a plus bi, where a and b are real numbers. So complex number is anything that involves imaginary or an imaginary part. And it's a 0 of the polynomial if when you plug it in, it makes the equation equal to 0. And sometimes it'll be asked by saying, where does the graph of the polynomial cross the x-axis? That's why we say it could be in a root of the equation as well. And I go back and forth. Probably 0 and root are the two that I say the most. I don't say solution all that often, but they all mean the same thing. So what makes an equation a polynomial? Well, first let x be your variable, and it's an equation that can be written in this form. Basically, you have a real number coefficient times x to the n plus another real coefficient times x to the n minus 1, so on and so forth, until eventually you just get down to plus a constant. Now, outside of an, which cannot be equal to 0, and the reason it can't be equal to 0 is we name polynomials based on what the highest power is. So you don't want to go through and say it's like if I gave this one like 3x squared plus 2x minus 3, or even to be more specific, let's say to show that you can let some of the middle ones be zeros, if it was 3x squared minus 1, I wouldn't say this is a third degree polynomial or a fourth degree, because it doesn't make sense to say, oh, this is 0 times like x to the fourth plus this. You wouldn't do that in this case, because you always name these by the highest power. So just remember that whenever you're naming them or looking at these. So it's perfectly okay to have like x to the 100 and then minus 2x to the 50 and then plus 100. That's okay, and you would say that's a 100th degree polynomial. These middle ones, well, basically even everything below the highest power can be 0. And then we, like I said, we name it by the degree, but we also can pull a lot from the leading coefficient, which is what's the constant that's multiplied to the highest power of x. And so in this case, if there's nothing written down, remember that's just the same as saying 1 times x to the 100. So we would say this is a 100th degree polynomial with a leading coefficient of positive 1. So first thing we'll do is test and see if the given number is a root to the polynomial. And this is kind of, or to the given equation. But when you first look at it, you may go, okay, what does this have to do with a polynomial? If I were to get everything on one side, so say I reordered this to be negative x cubed plus 6x squared, and then I subtracted over 5x and I subtract it over 12. Now the question is more in line of what you would think of. I'm saying, does this make the equation equal to 0? And a lot of times you can take two different polynomials, set them equal to each other, and you're technically, when you set them equal to each other and you say, okay, I want to know where do these two intersect, that's also very similar to finding what is the root of this given polynomial, where you would move everything to one side. So similarly with the second equation. So first thing we want to do though is we're just testing to see if this is a root. So first thing I'll do is I'll just plug in 4 to both sides, and I'm going to keep this question mark here throughout because I'm testing it. I don't know for certain. So if I do this, I get 6 times 16 minus 4 cubed would be 64. And you don't have to leave it in parentheses, but say this had been -4, then whenever I cube this, I'm going to get minus a minus 4, or minus 64, which would have been plus. So just be aware of certain things like that. And so then this would be 12 plus 20. Again, I'm going to keep the question mark there because I'm still testing to see if this is true. So the right side is going to be 30, no, not 32, or not 36, 32. And then 6 times 16 is going to be 96, because so one of the ways that I multiply larger numbers is, instead of doing 6 times 16, I say that this is 6 times 10 plus 6. Because then you can just distribute the 6 to like this, and then I know this is the same as 60 plus 36, which is how I was able to get to 96. At least in my head, that's how I'm able to do it. And then we have 96 minus 64, which does in fact equal 32. So in this case, x equals 4 is a solution to where these two polynomials intersect. Or if you went back to the way that we wrote it in the previous one, you could say it's a solution to where this polynomial equals 0. Just two different ways to think about it. Now notice this one though has an imaginary part. This one's a complex root. So one thing to keep in mind about if you have a complex root, what that means is there isn't, or this is a place where it actually does not cross the x-axis. Because let's say you have your graph here, and then you do a graph like this. In this case, this has no x-intercepts because it doesn't cross the x-axis anywhere, so that means it doesn't have a root. But, and this is a theorem we'll talk about later, whatever the highest power is, you have that many roots of the polynomial. The key thing is, though, just because you don't have all of them being real doesn't mean that they aren't there. This is a complex root. So when we test this, we need to see, does this satisfy this equation? Which would be the same as saying, does x squared minus 2x plus 5 equals 0 when I plug this in? So if we're going to multiply this, I'm going to have to do, technically this is 1 plus 2i times 1 plus 2i. Now, when I multiply numbers like this, some people are okay doing the FOIL where you write it like this and you have them side by side. I prefer to do what some people call as a lattice, or They say it's the box. And this is where you just write the terms like this. And then you just multiply the rows and the columns together. It's also very helpful because once you get into multiplying roots or multiplying factors of polynomials, so like maybe you would have x minus 3 plus I times x minus 3 minus I. When you do this, trying to do that, well, you can't do FOIL because it's more than two terms, but you could draw this box to be a 3 by 3, and then everything lines up a lot neater. So I recommend using this method for, oops, started erasing the wrong thing. Use this method for multiplying complex numbers. If you're more comfortable with another way, that's fine, but this is just a way to at least try. So 1 times 1 is 1. 1 times 2i is positive 2i. Technically, I don't have to write that it's positive. And then 1 times 2i is still 2i. But then 2i times 2i is going to be 4 times I squared. Now, first of all, remember I is equal to the square root of -1. Because it's an imaginary number. You can't have the square root of a negative. So that means if I square I, technically I'm squaring the square root of -1. And anytime you square a square root, you just are left with what's on the inside. So this part is actually equal to -1. So I didn't draw this small enough or the box big enough to write it on the inside. But this is going to be 4 times -1. Or just more simply put, -4. And then the nice thing is, if these work out correctly, then the diagonals typically line up to be the elements that you can combine. So, like this one, I add the top left and the bottom right, and I add the top or the bottom left and the top right, which is going to give me, so let's see, 1 minus 4 would be -3. And then that's going to be plus 4i. And then does that equal? So distribute the 2. So we get 2 plus 4i minus 5, which if we combine, we do end up with -3 plus 4i. And so if you needed a word answer for this, you would say x equals 1 plus 2i is a solution to the equation x squared equals 2x minus 5. So this would be if you needed to give a word answer to it. And again, technically what this means is if you were to graph x squared minus 2x plus 5, you would actually see that this does not equal 0. So that's one thing to be aware of, is if these two, or if this equation is balanced by an imaginary number or a complex number, then this does not have a solution. That's for if it's x squared. Now, if it's x to the 4th, that means there are 4 roots. So you could actually end up with a few that are imaginary and a few that are real. So just keep that in mind when working through these. And so to go off of, well, how did I know how to sketch it? We get to, a lot of times this is referred to as end behavior. So the end behavior of polynomials is x goes to positive or negative infinity. Now, to determine the behavior, all you need is the leading coefficient and the power of the polynomial. So this is kind of the wordy version. So I prefer the pictorial version, which I'll show you in a second. But basically, when you read this in words, what it says is if an is positive, then as x approaches negative infinity, p of x approaches positive infinity. This arrow here just represents approaches, or goes to. X goes to negative infinity, p of x approaches positive infinity. Typically, if you say 1, make sure you follow that up as the same one. That illustration is just kind of to show you what they mean. But what you read it is this graph rises to the left and rises to the right, versus the odd version where as x approaches negative infinity, p of x approaches negative infinity. And as x approaches positive infinity, p of x approaches positive infinity. So if n is odd, this is something like x cubed, x to the fifth, yada yada. And then if n is even, this is like x squared or x to the fourth, those kinds of deals. Now, let's say you were to encounter this function. So f of x is equal to x to the fourth, or let's not do x to the fourth. Let's write it this way. F of x equals x cubed, or x squared plus x cubed. Now you have two different functions. Which one do you go with? If this is the case, then you always name it, remember what I said, by the highest power and the leading coefficient. So even though x squared is written here first, x cubed is the highest power. And this is a positive 1. If there's nothing written there, it's just understood to be 1. So I'll have these separated. So this is what that looks like first. So notice as x goes towards positive infinity, so we refer to positive infinity as going to the right and going up, because what those values are is that your function is either increasing, which means you're going towards positive numbers, or decreasing, which means it's going towards negative numbers. So notice this one, it rises to the right and rises to the left, versus the odd one where it falls to the left and it rises to the right. Now, if both of them are negative, this is the key, or if the leading coefficient is negative here, this is a key differentiator. Notice when n is even, though, they both still approach the same thing. That's the nice part about having an even function. An even function will constantly go to the same value on both sides. The odd function will go to the opposite values. And so if the leading coefficient is negative and the power is even, then it falls to the left and falls to the right. So as x goes to positive infinity, the function goes towards negative infinity. As x goes towards negative infinity, the function goes towards negative infinity. Make sure that you read it as you go to the right or as you go to the left. Positive infinity implies going to the right. Negative infinity implies going to the left. So as x approaches negative infinity, f of x approaches positive infinity. Because if you follow this trail, it goes up like that. As x goes towards positive infinity, f of x goes towards negative infinity. And so if you put those together, this is the easiest way for me, at least, to visualize this. And the nice thing is, what it says is every polynomial function only has 4 basic shapes. It either is a leading coefficient that's negative with an odd or an even exponent as the highest power, or it has a leading coefficient that's positive and it has a power that's odd or even. And you may look at this and go, well, I've seen functions that are not as nice as this. That is true. One thing, if you really want to, you can just do like this. You can say that this is your graph for negative infinity, or for a negative and even power. And then you could say this is your graph for a negative leading coefficient and odd power. And then you could do something similar for a positive one. The reason for this is just to illustrate mainly where the tails of the function go. The tails of the function are your key thing. We'll determine everything in the middle kind of as we go. But first thing is, don't be immediately confused by only, like here, this has 1 turn, this has 2 turns, something like that. Just think that this is mainly here to illustrate the left and the right. Where do they go as they go towards infinity? So we're going to do sketches of these polynomials, and we're going to pay particular attention to their x-intercepts, their y-intercepts, and their behavior as x goes towards positive and negative infinity. So let's start with this first function. So yeah, we'll start x-intercept, y-intercept, and then in behavior. So x-intercepts. Well, this one's already kind of nicely laid out in that it's already in factored form. And because of that, I can just go ahead and I can set each part equal to 0. So originally I would set it up like this. I want to know where this is equal to 0. Well, to do that, we set each individual component to 0, because if multiple things are multiplied and one of them is equal to 0, if multiple things are multiplied and it equals 0, you know at least one of the things has to be equal to 0. Because I can't multiply 2 non-zero things together and get 0. You can add 2 non-zero things together and get 0, but you cannot multiply 2 non-zero things together to get a 0. So I would go negative x is equal to 0, 2x plus 1 is equal to 0, and x minus 2 is equal to 0. So once we're to this point, all we have to do is just solve for x. Now this one is pretty straightforward. If negative x equals 0, positive x equals 0, so we have 0 as one of our points, or roots I should say. If I subtract over the 1 and then divide by 2, I get that x is equal to negative 1/2. And if I add 2 to both sides, for this one, I get that x is equal to 2. So our roots are, or x-intercepts, are going to be 0, 0, negative 1/2, 0, and 2, 0. So notice these points are all, y values are 0, and the x-coordinate is what solved the equation. So we can go ahead and just put those points on the graph. So 0, 0 is nice. Negative 1/2, roughly there. And then 2 goes there. Now the y-intercept's a little bit boring in this case. To get the y-intercept, you just plug in 0, because that tells you where it crosses the y-axis. But in this case, we have negative 0 times 2 times 0 plus 1 times 0 minus 2, which all that is going to be equal to 0. So this is a very interesting case where the x-intercept is also one of the y-intercepts. If you ever have just x to a power factored out front, then that's always going to be an indicator that 0, 0 is your y-intercept. But now, this is where things are going to... This is where the in behavior is going to come into play. So in behavior. So the main thing is we need a sub n times x sub n. We need that leading coefficient with that highest power. But if you notice, we don't have it all multiplied out. It's in factored form. So how do you get it? So in order to get this, you just take everything that's attached to an x and multiply it together. So basically, you drop any pluses, or plus a number, or minus a number. You leave this minus here, because that's going to be important in a sec. So negative x times 2x times x. So that equals negative 2x cubed. So what we have, that curly bracket turned out very poor. We have that n is equal to 3. And a sub n is equal to negative 2. So if you go back to the chart, I'm not going to scroll back to it, but what we have is a odd power with a negative leading coefficient. So what that means is it's going to have something like this shape. And again, middle doesn't matter. Middle is just there to indicate that changes can happen. So the main thing I know is that it's going to have to rise to the left and fall to the right. So in order for that to occur, I've got to do something like this. And then this is going to do something like this. Again, I'm just sketching it. I don't have a full-on idea of what it's going to look like, but there's just a good sketch. One kind of takeaway here is, notice if I had not done the check, I could have actually graphed this. I could have done like this and made it come up through here. That would have been a way that I could have graphed it. Or I could have said, well, maybe it just goes through this point, bounces off that point, and it does something like that. But that's the key with the in behavior. The in behavior is guiding the graph as to where it needs to go. So always take the in behavior into account. So now what if we do x squared plus 2x plus 3? Or minus 3, sorry. So again, we'll start with x-intercepts. Difference here is it's not factored yet. Jumped ahead to the end. X squared plus 2x minus 3 is equal to 0. So first thing I've got to do is factor it. Now, everybody has their own way of factoring. You can do the quadratic formula. You can complete the square. I don't recommend completing the square here. Just standard factoring. Slide divide everybody has a way. This case is just kind of your normal factoring. So usually what I do is I just draw an X and I say, okay, what two numbers, because remember, you're going to multiply two numbers to get this last one and add two numbers to get here. So what multiplies to get me -3? So this is multiplies. I'll just use a little star for that, or asterisk. And then what adds to get me +2? So what two numbers fit that bill? Well, if I'm going to multiply and get a negative, one of them is going to have to be positive and the other is going to have to be negative. So the only two things that are going to multiply to get me -3 are if I do 3 and -1 or 1 and -3. If I did -3 and 1, those would add to get -2. So I'm going to have to do +3 and -1, because if I multiply them, I get -3, and if I add them, I get +2. So then that gives us x plus 3, x minus 1, not 2, is equal to 0. Like before, set each term equal to 0. So that gives me x equals -3 and x equals +1. So our x-intercepts are going to be, if I don't write them backwards, they're going to be -3, 0 and 1, 0. So -3 goes here, +1 goes there. Now the y-intercept I'm going to use a different color for. And again, to get the y-intercept, it's a lot easier. You just plug in x is 0. So that gets me 0 squared plus 2 times 0 plus 3 minus 3. The hard part about writing and talking is saying the right thing while you split your brain to do another task, which is just going to leave you with -3. So in this case, our y-intercept is the point 0, -3. So that'll go down here. And then finally, the end behavior. So again, what is an x to the n in this? What's the highest power? Well, the highest power is 2. So we have x squared, which is going to give us that n is equal to 2. And a sub n is equal to 1. So this is an even degree with a positive leading coefficient. There we go. Which means that both of them, because it's even, remember, they both open the same direction, and because it's positive, they both open up. So this is going to go something like, and if you need to get some extra points to graph the function, that's fine, unlike that weird like curve that I put in the graph. So you would get something that looks kind of like this. And again, we base that off of the leading coefficient and the degree. So 3 steps for graphing. Get your x-intercepts, get your y-intercepts, y-intercept. You should never have more than one y-intercept. If you do, that's no longer a function. and then check the end behavior, because the end behavior helps guide you. If you want to, you can always plot a few extra points. I'm doing this with as few points as possible. The x-intercepts and y-intercepts are all I'm trying to use just to indicate that you just need that end behavior to finish the job from there. If you want to just kind of get a couple of extra points, yeah, you could pick like maybe x is equal to, 2. You could pick -1 since it's between those two. And it would just help kind of get you a good idea of where to graph these and where to put them. But that covers it for 4.1. We're going to continue, again, continue more with polynomials. We'll do some more factoring techniques, and we'll just continue on with this.